Going to continue with our operations on complex numbers. Today we're going to work on multiplying and dividing. To multiply, you're just multiplying as if it were a variable. But the thing you want to keep in mind is we do know that I squared is equal to a -1. So we may wind up substituting some. In this instance, you're multiplying your numbers. 2 times 6 is 12, and you're multiplying your variables. I times I becomes I squared. I squared then gets replaced with a -1, so that's 12 times -1, or -12 for our final answer. We're going to distribute on this one, so that becomes an 18i. Here that becomes a 9i squared. We will replace, so our I squared becomes 9 times -1. It's plus there, by the way. So that's 18i plus a -9. We want the real part in front, though, so that becomes a -9 plus 18i for your final answer. Again, you're distributing here. That winds up being -5/2, because that's over 1, times I. And when you multiply here, that becomes a positive 40i squared. Every time your I squared becomes a -1, so that winds up giving us a -40 for our real part and a -5/2, or 2.5i. The last couple, we're actually going to have to distribute both terms to both terms in the second binomial. So when I do that, that gives me 12 plus 6i. And then I go here, and that's 8i plus 12i squared. Again, I squared becomes a -1, so this is a -12. When I combine my like terms then, 12 minus 12 actually goes away. Combine your imaginary terms, and you wind up with 14i. On the last one, just fractions, no big deal. You're distributing again. So that winds up being numerators multiply, denominators multiply, so that's 3/8. When I multiply 3/4 times 8i over 1, that gives me a -24i over 4, which hopefully you recognize that will reduce. That'll be a -6i. And then distribute the -5i, so that's over 1. -5i over 2, or 5/2 I. When we multiply here, that becomes a positive 40i squared. Again, that I squared becomes a -1, so that this term is going to become a -40. We're going to combine our real terms, so the 3/8 and the -40 go together. That just becomes, you could do that as a -39, because subtract 1, and then that would leave 5/8. And you could make that, if you would like, humongo number over 8. Really, there's no point in finding a common denominator with that, since you're subtracting less than 1. On the last piece, when we put our imaginary parts together, that's a -6 and a -2.5, or a -5/2. I could change that to have a common denominator. That'd be a -12 over 2. So that's over 1 at the moment. So that becomes a -17/2 I. You could make that be a -8.5 I to go along with your -39 and 5/8. Right? Looking at the next piece, we're going to talk about conjugates. And if you remember, we talked about conjugates with radicals. On a radical, it simply meant that you were going to change that middle sign. So the conjugate would be 2 plus root whatever. In our case, that whatever is a -1, so that really would become 2 plus I. Same concept applies over here then. This is your radical, the square root of a -1, so its conjugate is simply 3 minus I. The imaginary piece changes signs to create the conjugate. we're going to utilize a conjugate in a fraction format, just like we did with radicals. And we're going to want to find the conjugate of the denominator, right? The numerator just follows along and multiplies out, but we want the conjugate of the denominator, which the imaginary part would change signs, so that would be 2 minus 5i on both the top and the bottom, right? So right now we just wanted the conjugate, that's what we're looking for. On part G, we're actually going to divide these out. So if we were thinking in terms of radicals, the conjugate here would be, you would simply multiply by the square root of -1. Again, to make that go away, that would create square root of -1 times square root of -1 would be a -1. On the top, you would get a root -1. Think about that we would replace this with an I over -1, or that would become a -I. If we treated that as the imaginary piece, its conjugate would be -I, -I. So on the top, 1 times -I would become -I. On the bottom, I times -I would wind up giving you a -I squared, which we know I squared is replaced with a -1, so that's -1, or -I over 1, which gives us the same thing that we got, right? If we strictly look at conjugates with the I in there instead of the radical, the imaginary part changes sign, so that would be a -2i over a -2i that I'm going to multiply by. 1 times -2i, of course, is that. On the bottom, the coefficients multiply, so that's a -4. The i's will multiply, that gives you I squared. So that's a -2i over -4 times -1. So we get -2i over a +4, reducing your fraction for a final answer of -I over 2, or if you wanted a -1/2 I. Either way of writing that. For our final one, with the binomial there, the complex number, we're going to use the conjugate again, which would be 2 minus I. 2 minus I. We'll do that both on the top and the bottom. We've got to distribute, so we'll get 10 minus 5i. We'll get a +2i and a -I squared. On the bottom, again, distribute, so we get 4 minus 2i plus 2i. That's the trick that always happened with our radicals. It's always going to happen here as well. That winds up being a -I squared. Canceling out or combining whatever you can, I'm going to substitute in place of my I squared a -1. So that's minus a -1 or plus 1. Here again, substitute that -1, so that's minus a -1 or plus 1. So it looks like we're going to, for a final answer here, the tops combine to give you 11. The imaginary pieces will give you a -3i. On the bottom, that's going to be 4 plus 1. And your imaginary pieces cancel each other out. So this will be our final answer for our division problem. And lastly, we're going to look at a little bit of graphing. These are things that we have been doing. So let's just kind of look through what we know. If I were going to graph this, I hope that you would think of that in terms of 25 times x minus 0 squared plus 100. It is in vertex form already. So therefore, our vertex would be 0 and 100, right? We know that it has a vertical stretch of 25. Super tall and skinny. And there is no reflection, so this one will open up, right? Knowing all that, I would go up to 0, 100. Well, that's going to be a problem on my graph, but I'm going to count by 100s. That'll help. So 0, 100, there's that. And if I do a vertical stretch, for every block I go over, because I'm counting in 100s both ways, so I can just say for every block I go over, I'm supposed to go up 25. So super duper way up here close on both sides. Obviously that's nowhere near 25, but that's going to give you something that's going to look like that. Really tall and skinny, opening up, and we're asked to solve on this. Remember, when we're solving, we are looking for x-intercepts. We have no x-intercepts. If you have no x-intercepts, you can still get solutions. They're just going to be imaginary. And we've done stuff with this before.